Hello and welcome to another Arlington High School Math 4 Honors lesson. Today we're going to be doing Unit number 9, Lesson number 3 on the parametric form of a circle and an ellipse. So far we've gotten the general idea of what parametric equations are. And we've also seen how to form parametric equations for all types of lines, horizontal, vertical, and slanted. Again, only in 2 dimensions. We'll eventually do them in 3 dimensions in later lessons. But today what we're going to do is see how we can take equations of circles and ellipses and put them in parametric form. Alright, let's jump right into it. In exercise 1, I tell you that the following equation is the equation of a circle. Okay, so a circle is given by the parametric representation shown before, where the x-coordinate is given by this function, the y-coordinate is given by this function, and the parameter goes from 0 to 2 pi. It says, by hand, construct a table of values for this parameterization and use it to plot the circle, indicate the direction of the curve. Alright, so on the advanced placement calculus exam, we could easily see something like this come up. So let's come up with the equations, or not the equations, but let's fill out a table. And why don't we start by using what are known as the quadrantal angles, right? 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right? Now I'm going to do this pretty quick because at least for my students the expectation is that they know the sine and cosine of these angles pretty much almost immediately. For instance, if I put 0 in here, we know that the cosine of 0 is 1, so x would be negative 3 plus 5, right? Or 2. On the other hand, the sine of 0 is 0, so y would be just 2 plus 0, so y would be 2. In other words, we can tell that our circle, if you will, starts at the point 2, 2. That's our starting point. Now when we go to pi over 2, we know that the cosine is 0, so we'll get negative 3 plus 5 times 0, so that'll just be negative 3. On the other hand, the y-coordinate, right, sine of pi over 2 is 1, so we'll get 2 plus 5, and we'll get 7. So the point negative 3, 7, 4, 5, 6, 7 is also on our circle. At pi, the cosine is negative 1, so we're going to move along on this. We'll get negative 3 minus 5, which gives us negative 8. On the other hand, the sine is 0, so we'll get 2 plus 0, which is 0, so 4, 5, 6, 7, 8, and 2, right? 3 pi over 2, the cosine is 0, so we'll get negative 3 plus 0, gives us negative 3. The sine is negative 1, so we'll get 2 minus 5, which is also negative 3. So we'll be at negative 3, which is somewhere around there. And at 2 pi, we go right back to where we were at 0. Negative 3 plus 5, positive 2. 2 plus 0, positive 2, and we're back to here. So we start at this point. We come through all these points, right? And we have that path. Indicate the direction of the curve. Don't forget to do that. Don't forget to do that. It's easy. All right, now, letter B asks us to find an equation for the circle in center radius form, all right, that eliminates the parameter. All right, so it's been a little while since we've eliminated the parameter. We did that in lesson 1, okay? And what we're going to do, we're not going to solve for t and then substitute in. We're going to continue to use the Pythagorean identity, okay? Good old Pythagorean identity, not the Pythagorean theorem, although certainly the Pythagorean identity comes from the Pythagorean theorem. But remember, the Pythagorean identity just says that if we take the sine of an angle and we square it, the cosine of an angle and we square it, we'll always get the number 1 when we add them together. So we can solve that first equation for cosine t, and of course that will be x plus 3 divided by 5, right? We can solve the second equation for sine t. Sine t will be y minus 2 divided by 5. And we can now substitute these into the equation for sine and cosine. So for instance, we'll get y minus 2 divided by 5, quantity squared, plus x plus 3 divided by 5, quantity squared equals 1. Now I'm going to do something that's going to seem kind of weird at this point. I'm going to leave the numerators unsquared. So I'm going to rewrite these as y minus 2 quantity squared, but I am going to square the denominators. That's divided by 25, and x plus 3 quantity squared also divided by 25 equals 1. We could actually leave it like that. I think that's a lovely way to leave it. It's not center radius form. To get it in center radius form, what we would do is we would multiply both sides of this equation by 25, thus canceling those 25s, leaving us, let me actually write the x term first. Since it's addition, it does not matter. But I think most students are pretty comfortable with seeing this form of a circle, right? What's known as the center radius form of a circle. Right? We can easily tell from it that the center of the circle is at -3, 2 with a radius of 5. Now write that down if you haven't. I know that the problem didn't state that, but what I want to point out is that when we look at the parametric form of a circle, so let's come back up here and change it to red. When we look at this and we look at this, we can literally see both the center and the radius. Do you see them, right? Here are the coordinates of the center, right there, right? -3, 2. And here is the radius. And it really should make sense to people, right? Think about this. When we have a circle centered at the origin, what we've seen in a variety of different contexts is when it's centered at the origin, the x-coordinate is always r times cosine theta, and the y-coordinate is always r times sine theta. But the sad thing is those really aren't x and y. They're really the change in x and the change in y, right? So that's all we're doing here, and then we're adding those changes in x and changes in y to the coordinates of the center. And that's it. So a circle is very, very easy to parameterize. Now, I will have to say there are many ways to do it. As long as a circle, as long as you can use that Pythagorean identity and rearrange things, there's many, many different ways to form the parametric equation of a circle. But this is the most common way. Anyway, I'm going to clear out the text, so copy down anything you need to. All right, let's go on. Let's move on to the next problem. The parametric representation of a circle. So this is exactly what I was just getting at, right? If we look at the equation of a circle, right, whose center is at hk, and with a radius of r, we can always say that the x-coordinate is the x-coordinate of the center plus r cosine theta, and the y-coordinate of the center plus r sine theta. Very, very simple. So take a look at exercise 2. It says, give a set of parametric equations that represents the circle shown in the graph below. Then verify your result by using your graphing calculator. All right, so what I'd like you to do is write down the parametric form of the equations, okay? And then we'll deal with the graphing calculator together. All right, should be easy. What's the center? The center is right here, and that has coordinates of 1, -3. The radius, pretty easy to tell, is 2. So the simplest way to parameterize this circle would be 1 plus 2 cosine t, and y equals -3 plus 2 sine t. Now it's important to give this where t is between 0 and 2 pi. You can actually leave off the equality on the 2 pi. It's kind of redundant, so that little guy. But I tend to just throw it in for kicks and grins. Now it is important that you have that interval, because if you don't have the full interval, you don't get the full circle. Anyhow, let's take a look at what this looks like on the calculator, as well as exploring the problem a little bit more. So I'm going to bring out the TI-84 Plus right now. All right, welcome back, calculator. All right, we should be in parametric mode and all of that, but let's check it anyway. Hit your mode button. Check that you're in parametric mode. All right, get back out onto the main screen. Let's go into y equals. Let's clear out anything that we might have in x1, t and y1, t, probably from the last lesson. All right, and now let's throw those in. So let's go into x and let's type in 1 plus 2 cosine t, and y should be -3 plus 2 sine t. Now, one thing that occurs to me right now is our calculator in radian mode, right? We could do this in degrees, but the interval specifically says 0 to 2 pi, so we're going to stick in radians. So let's hit our mode button. Make sure that we're in radians. Check that. If you're not in radians, please put yourself there. Okay. Let's go into our window now. All right, what's great about this is it's very obvious what our t window is, right? Our t min has to be 0, so let's put that in. Our t max really should be 2 pi. Let's put that in. Maybe we'll experiment in a little bit to see what happens if we change that. All right. Delta t, might as well leave it the way it is. X min, X max, well, why don't we try to get the picture that's on the screen? It looks like X minimum is -6 and X maximum is +6. Y minimum, -6. Y maximum, +6. Okay, make sure that we have all that set, and let's hit graph. Okay, it takes a little while as always, but it's kind of cool. You can even kind of tell that it is starting at that due east point and then moving counterclockwise, right? And tracing out that circle. You know, there's that extra question, why does the graph not appear circular in your calculator, right? It looks more elliptical-like. And that's simply because the scale on the x and y axis isn't the same. All right, and that's always a bit disturbing. Now, before we move on to the next exercise, let me just show you a few things. Let's go back into the window really quick. Let's change it so we're not going 0 to 2 pi. Why don't we go to 0 to 3 pi over 2? I bet you can already predict what's going to happen here. If I hit graph, right, look what's going to happen. Right? It's going to stop short. It's going to stop down there at 270 degrees or -90, depending on how you want to look at it. All right. Now I'm going to be real crazy for a second. I'm going to go into y equals. I'm going to actually change that cosine t to a sine t on x. And I'm going to change the sine t to a cosine t on y. I'm going to go back into my window right now. And I'm going to go back to 0 to 2 pi. Okay. And now I'm going to hit graph. And what's really amazing about this is we're still getting a circle. Granted, it's not starting in the same place, right? But it's still the same circle. The remarkable thing is that the most common way of parametrizing a circle is using cosine for x and sine for y. But the plain fact is you could use cosine for x, sine for y, sine for x, cosine for y. You can't use cosine for both or sine for both, all right? But changing one for the other will not change what circle you have, but it will change the point that you start at and the direction you travel in. And we're going to explore that more later on. I would suggest for right now kind of memorizing that form and using it, because it will always guarantee that you will start at due east and that you will travel counterclockwise. Getting it to start at a different point is not all that difficult. In fact, we could just change the time that we start at, the angle that we start at, and that would then change which starting point we have. Anyway, I'm going to clear out the text now, so copy down anything you need to. All right, here we go. All right, let's move on. Ellipses. All right, so ellipses in Cartesian form generally have this equation. Cartesian form, right? Cartesian meaning that there's both x and y in the equations, okay? H is still this, h kind of k is still the center. The big difference is those a's and b's give what are called the length of the minor and the major axis. So a, if you will, is sort of the radius in the x direction. B, if you will, is the radius in the y direction. See, all really an ellipse is a circle that's been squished or dilated. Or all a circle is a specialized ellipse. It's kind of like an ellipse is to a rectangle as a circle is to a square, if you kind of follow. All right, so let's play around a little bit with ellipses, see what we can do with them in parametric form. Now, in exercise 3, I say this thing's an ellipse. 3 plus 5 cosine t and -1 plus 2 sine t. I bet you can already figure out why it's an ellipse and not a circle. But let's play around with this exactly the way that we did before. Let's create a table by hand using just those quadrantal angles, and let's track this ellipse. All right, let's start with t equals 0. Again, let's do this pretty quickly. If I put 0 in, the cosine of 0 is 1. I get 3 plus 5, and I get 8. If I put 0 in here, sine of 0 is 0. Y will be negative 1. Let's get the entire table, and we'll start kind of drawing out the graph. If I put pi over 2 in, cosine is 0. X would just be 3. Sine is 1. Y would be 1. If I put pi in, cosine of pi is negative 1, so I'll have 3 minus 5, which will be negative 2. Sine of pi, though, is 0, so I'll have a y-coordinate of negative 1. If I have 3 pi over 2, the cosine is 0, so the y-coordinate is just 3. The sine is negative 1, so here the y-coordinate is negative 3. And if I come full circle, pun entirely intended, at 2 pi, the cosine is 1, so y will be 8. Sine will be 0, so y will be negative 1. So let's think about this a little bit. Our biggest value of x is 8. Our smallest value is negative 2. I just want to think a little bit about my axes here before I kind of draw them out. That should be pretty good, right? Because what do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, negative 1. And remember, that's our starting point. Then I have 3, positive 1. Then I have negative 2, negative 1. Then I have 3, negative 3. And then I have 8, negative 1. So there's our ellipse, right? There are our arrows that indicate the direction that we're traveling in. Okay. Now, you know why it's an ellipse, right? I mean, this looks almost identical to a circle, but the big differences, right, are that the 5 and the 2 are now no longer the same number, right? Those numbers, the 5 really gives you this length, right? It tells you the maximum extent you go in the x direction away from the center. And the 2 gives you this length, the maximum distance you go away from the center in the y direction, right? If you will, this is probably not standard notation, but the radius in the x direction is 5, and the radius in the y direction is 2. Now let's come up with that Cartesian equation, right, by eliminating the parameters. And we're going to still use our friend, the Pythagorean Identity. So maybe I'll write down the x term first. Cosine squared t plus sine squared t is equal to 1. If you're one of my students, I require you to write all these steps, so don't skimp, okay? Don't skimp. I want to see it all. Cosine t is x minus 3 divided by 5. Sine t is y plus 1 divided by 2. We can now throw it into our Pythagorean identity, which is always true. X minus 3 squared plus y plus 1 divided by 2 squared is equal to 1. Kind of like with the circle, I'm going to leave the numerator unsquared, or in that form, but square the denominator. And same thing here. This is what's known as the standard form, the standard Cartesian form of an ellipse. All right. Anytime you have an ellipse, you prefer to write it like this, right? As we saw before, very similar to the equation of a circle, except in the equation of a circle, we don't tend to have it set equal to 1. We tend to have multiplied through by a common denominator. Here, we can just leave it like this, because we can look and say, oh, all right, well, the radius in the x direction is the square root of 25. The radius in the y direction is the square root of 4. But that's it. There's our Cartesian equation, right? So very simple, I hope, right? With both the ellipse and the circle, we start by saying, hey, look, we have a center. And the question is, what is the maximum extent we go in the x direction? What is the maximum extent we go in the y direction? I'm going to clear this out. All right, let's go on to the next problem. There it is. Everything summarized for you with a lot of letters, right? An ellipse centered at h comma k with a horizontal axis of 2a and a vertical axis of 2b has those parametric equations. So let's do one final beast. says, given the ellipse whose equation is 25x squared plus 100x plus 4y squared minus 48y equals negative 144, write it in standard form, that's the way we just wrote it, identify its center, and give its parametric representation. Wow. Okay, well, let's write this beast down. This is a fun algebraic manipulation, and by fun I do mean it is fun for me. We need to get this thing and manipulate it somehow into a form that looks like this. And there's probably many, many different ways we could go about doing it. What I'm going to start with is I'm going to start by completing the square. Now, in order to do that, I have to factor out a 25 because I need a leading coefficient of 1, and I need to factor out a 4 because I also need a leading coefficient of 1. Now, let's review completing the square. Remember, if I have a leading coefficient of 1, I can take half of the b term, which would be 2, square it, and add it on. So I add on 4. Now, normally I would add on another 4 over to this side of the equation, but what I've really added to both sides of the equation is a 100. I'm going to just get rid of this for right now. Okay. The reason I've added a 100 is I've really added 25 times 4. Likewise, within this parentheses, right, if I do 12 or negative 12 and I divide it by 6 and I square it, I'll add on 36. But over here, I really should be adding on 4 times 36, which is 144. So that's just 4 times 36, in case you're wondering where it came from. So now the beautiful thing is I can write this as 25 times x plus 2 squared. This I can write as 4 times y minus 6 squared. And here, when we tabulate everything up, what we'd end up having is just 100, right? Because these two would cancel. Now, remember, what I want is something that looks like this. X minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. So I need to have a 1 over here. So there's really only one thing I can do, which is divide both sides by 100. That'll give me x plus 2 squared divided by 4 plus y minus 6 squared divided by 25 equals 1. So that is, whew, believe it or not, the answer to this part of the question. Wow, man, makes my hand hurt, so much writing. Okay. Now, we want to identify its center. That's going to be pretty easy, right? That's going to be negative 2, 6. And we want to write its parametric representation. Well, this is where I think it's helpful to think about it like this. I think it's helpful to say, hey, the radius in the x direction, well, that's 2, right? This is 2 squared. And the radius in the y direction, well, that's 5, because this is 5 squared. So what I can now say is that the parametric equations are the center plus 2 times cosine t, and y equals the center, 6, plus 5 times the sine of t. I should probably state that t goes from 0 to 2 pi. Otherwise, I won't get the full ellipse. All right, or I'll get too much. So that's it. There is the parametric form of this particular ellipse. It's kind of amazing, isn't it? That the information contained in this equation and the information contained in that equation really are the same. It's kind of cool. It's kind of cool. All right, I'm going to clear out the text. You know, I would encourage you to put that last ellipse into your calculator and make sure it looks the way you think it should. Okay, but I'm going to get rid of this. All right. So in the next lesson, we look at our last type of curve, which is a hyperbola. That's a little bit harder, simply because hyperbolas are harder. They involve subtraction. Anyhow, until that time, let me just remind you that this is an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, And until next time, keep thinking and keep solving problems.